The second fundamental theorem of calculus. The main thrust of this theorem is actually found in this simple statement here. If you look carefully, right, what it says here is if you were to differentiate an integral, then you get back the function fx. What's important to note is in this derivative, right, you are differentiating with respect to x, and x must appear as the upper limit. So this theorem says if you were to differentiate an integral, you get back the function itself. In fact, that's something you would expect because you've done a lot of differentiation integration. You know that if you differentiate your integral, something you've integrated, you get back itself. The formal statement of this is found here, that f is a continuous function on the interval I. If you're continuous, right, you have an antiderivative on the same interval. And then if you have a point A that's inside I, then this expression is actually the antiderivative of the function f. Antiderivative also has a meaning that if I were to differentiate the antiderivative, like this, right, I'll get back the function fx, sorry, right. Antiderivative means also has the same meaning that if I differentiate antiderivative, I get back the function fx. So in the long and short, the second fundamental theorem of calculus actually says this. It's a very high sounding theorem, but actually it's quite easy to apply. Let's look at some simple example. In example 38, right, you have to differentiate this integral. In this integral, you're integrating from 0 to x. You can see 0 to x. The upper limit is x. So this theorem says if you were to differentiate this integral, you get back the function itself. You can see. Now you see that the x takes the place of t here. You can see. Likewise, if you were to differentiate the integral, right, the upper limit is x. It doesn't matter what you have on the lower limit. So the theorem says differentiating this integral, you get back fx. You can see t is now replaced as x. In the third example, you notice that x is actually on the lower limit. And to use that theorem, right, to use theorem, x must be an upper limit. But we know that we can actually turn this limit the other way around by introducing a minus. So using the result of the theorem, I can now say that this becomes, differentiating this, right, you can see it's fx again. Of course, the minus flows through here. For another example, we might have to use so-called the chain rule. What is chain rule? Dy dx is equals to dy du times du dx. How do you apply chain rule to more different examples? Let's say this one. You want to differentiate respect to x, but you can see that now it's x cubed. It's no longer x. When that happens, you can do it by so-called chain rule. You let u be x cubed. So then du dx is 3x squared. How do you apply the chain rule? D dx, right, is now changed to d du dx. So now the x cubed now is replaced as u. Can you see? And now this expression looks like what we have in the theorem. Differentiating this expression gives you just, in place of t, I put as just u. And du dx is 3x squared. Now I put back the u back as x cubed. I get x cubed to the power of 3. So give you x power of 9. You could do this question quite quickly from here to here. No? Actually, what you can do is you just replace all the t with x cubed, and you just times by the derivative of the x cubed. You can see you can get from this line immediately by simply replacing the t as x cubed, and then here is your differentiation of your x cubed. But otherwise, you can just use the substitution and of course the chain rule. Likewise, in 39b, right? If I do not do all these things, okay, if I do all these things, I could actually do this question quite quickly by replacing the t with tangent x, you can see. And then I just include a derivative of the tangent x. So you do this way, it's very fast. That you can get from this line to this quite quickly. One thing you must note is before you use the theorem, you must make sure that things work well. Like for example, if you choose an interval from -10 to x cubed, then this integral has a little problem, right? Because this function is not defined, say in the case when t is -10, or when t is actually even like -9, even to be defined. So when that happens, you cannot really use the theorem because something's wrong about this, right? Let's look at more examples. Now you have minus x here and x here. For such a question, right, you will break it up into two parts. Minus x to 0 and 0 to x. I can turn this the other way around by putting a minus here. And now we're ready to apply the theorem. What's the theorem say? To differentiate this expression, you just replace the t as x. Can you see? Replacing the t as x. Likewise, to differentiate this expression, I replace the t with minus x, and then I differentiate the minus x here, I get -1. Upon tidying up for part C, right? Upon tidying up, you just get this answer. Likewise, in part D, you can break this integration into two parts. 0 to sine x cubed, and then, x to 0 and 0 to sine x cubed. And once again, you can change the limits. And now once you've done the change, you can differentiate this one by replacing t with sine x cubed, and then you introduce the differentiation of sine x cubed here. And this one just replace the t with x, and this is your final answer. Now let's do the next example, example 40, which is taken from a past AP exam paper. In this question, you're given a function that's made up of a straight line and then a curve. And it's described here that this function is twice differentiable, and the second derivative is positive over the interval from 0 to 6. What this means is, over the interval from 0 to 6, the gradient is actually increasing. Indeed, it is right. Over here is very negative gradient, less negative, 0 gradient, positive gradient, and more positive gradient. So which tells you this condition given to you. So part A of this question asks, is f differentiable at x equals 0? At x equals 0, which is here, you see a curve here, right? A sharp turning. So judging from this graph, right, you can therefore tell that that this function f is not differentiable at x equals 0 because of the presence of a curve. Next part of the question asks, they want the average rate of change of f over this to be equal to 0. Let's recall, how do you find the average rate of change of a function? To find the average rate of change of a function, you gotta find the value of f6 minus f of a, then divided by the interval 6 minus a. Okay, once again, to find the average rate of change, right, you gotta find f of 6 minus f of a and divide by the interval of 6 minus a. In order for this rate of change or average rate of change to be 0, it means to say f of 6 minus f of a has to be 0 itself, which means f of a must be equal to f of 6. So let's look, in this graph, are there other values that will give you the same value as x equals 6? But x is 6 is 1, right? So are there values that will give you f of a equals 1? I think roughly, here, f of 1 is roughly equals to 1. So there's one point here, roughly here. Then draw on some more, and there's another point here. Roughly at minus 1.5, you find that f of minus 1.5 is roughly also equals to 1. So judging from graph, Answer to part B is, therefore, there are two values of A, but we can't be sure which two values. In part C, you want an interval that guarantees a gradient of 1/3. So which means to use the main value theorem, you must be able to find a point A and then with 6, right? A point x was A and a point x was 6, where the gradient of the line joined together is equal to 1/3. So this is the point when x is 6. I need another point that makes a gradient of 1/3. So from here, right, if from x to 6, if I draw a line that's like this through this point 3, 0, the gradient is 1/3, can you see? So which is actually this gradient that you intend to have. So the answer part C, right, is there a value A? Yes, there's such a value A, and the value A in this case is actually 3. If you apply main value theorem over this interval 3 to 6, right, it assures you a gradient of 1/3. Right, between this point and this point, the gradient is indeed 1/3. Then next is part D. Part D is where you have to use the second theorem. In this part D, you ask now, what interval does G concave upward? Okay, for G to concave upward, right? Concave upward means it's a U shape, and concave upward also means that the gradient actually increases. So what I'm going to do is, if I differentiate this Gx here to give you G prime, differentiating this on the right hand side will just give you, remember the second term says if you differentiate an integral from 0 to x of ft, right? Differentiating this will just give you fx, which means the gradient of g, which is g prime x, is just equals to fx. So to find where the gradient is increasing, I just have to find where fx is increasing to conclude where g concave upwards. So looking at the graph, right, fx actually increases from -4 to 0, that's one interval, and fx also increases from 3 to 6. So therefore, I now know that the graph concave upwards over the interval -4 to 0 and over interval from 3 to 6. Right. The working for these parts are shown here. I'm going to scroll down slowly and you can jot down. This is A, B, and C. So give some time to jot down first. And then part D. Now let us do example 41, which happened to be the last example of the chapter 3 notes. In this example, you are told of a company that makes cable. For every meter it sells the cable for $120, which means for 2 meters you sell it for 240, for 3 meters it will be 360. And of course, a company that produces cable will also incur costs in producing the cable itself. And you're told that that the cost of producing cable, right, actually varies with the distance from the beginning of the cable. What basically is happening here is, you know that if you have a very long wire, to make it even longer, it can be quite costly actually. You know what I mean? So if you're making a very short wire, actually it's quite cheap. But once you make a very, very long wire, and to make it even longer still is actually quite expensive. To give you another analogy is this, no? to buy a small mirror is quite cheap. But to buy a big mirror, right, the price can go quite high. If you have a big mirror and you want a even bigger mirror, I think the cost is even more expensive. So it's not easy to produce big mirrors. It's actually quite costly. Right? So that's what the author trying to say here, that the cost of producing the cable is not constant throughout, which is the case in most of the time in such industry. And you are told that the cost to produce a portion of cable X meter long from the beginning of the cable is 6 root X dollars per meter. So what this sentence actually mean is like this, no? That if you already have X meter long, to produce an additional meter from it, right, you need to pay 6 root X dollars for every meter. Okay. So there's this definition of profit. In fact, it's quite intuitive. Profit is always equals to the revenue minus the cost price. The revenue is how much you collect by selling the cable, and the cost price is the money that's spent to produce the cable. And this question comprises 4 parts: finding the profit from selling 25-meter cable, and then asking for meaning of this integral, and then part C, and then part D. So let me read for the lower first, and then we can do it together. Okay, to start with, right? Let's get this thing cleared up first. So as I told you just now, this statement, right? This statement means that you already have X meter long, and beyond that, to make every 1 meter, to make the cable 1 meter longer, it costs you 6 root X. So from this, what we can see, if you already have a cable that's already very long, that means this X is very big. To make 1 meter longer than that, right, they find actually it's quite expensive, right? And what's important to note is this sentence actually means that the rate of change of the cost in producing a cable is actually 6 root X. As I told you, cost of production is not uniform. It depends on the length of cable you already have, and then to produce longer than that, right, it get more and more expensive. If there's a rate of change of cost with respect to X, and then performing integration, the cost of producing L meter long will be given by integrating from 0 to L of this expression. Okay, so with this, we are now ready to actually answer the 4 parts to this question. Part A asks you for the profit, Part A asks you for profit in making or in selling 25-meter long. For every 1 meter, I sell for $120. So for 25-meter, I sell it for this much money. And then the cost of producing 25-meter long, right? Remember, we had this expression just now, 0 to L. Now L is 25. This is the cost of producing the 25-meter long wire. So revenue minus cost price will give you the profit. So check my values, make sure that you get something. Then in part B, they ask you for the meaning of this expression. So this expression, if you look carefully, right, you can rewrite this thing as integrating from 0 to 30, 6 root X, minus integration from 0 to 25, 6 root X. You could rewrite this expression that way. And then if you rewrite in that way, right, you can see that actually there's a difference in cost in producing a 30-meter long as compared to a 25-meter long wire or cable. You know what I mean? Let me say once more, okay? This integral, right, you could rewrite this integral as 0 to 30, 6 root X, minus 0 to 25, 6 root X also. So by seeing this way, you can therefore see that it's actually a difference in cost in producing 30-meter and a 25-meter long cable. So now if you have a K-meter long cable, right, this is actually the selling price, and this is actually the cost price of making it. And this expression tells you the profit that you get, or the PK, express it means profit as a function of the length of the cable you are making. So of course, as in all businesses, you want to maximize profit, which means you want to maximize this quantity. To maximize this quantity, right, the usual way is to differentiate the quantity and then equate to 0. By differentiating this, right, differentiating 120 k just give 120. To differentiate this, remember the second theorem says if you differentiate 0 to x, 0 to k in this case, 0 to k, 6 root x dx, you just get 6 root k. This is from the second theorem. So you equate this to 0, and then you get the value k equals to 400, which means this is a possible candidate where you can actually attain a maximum profit. So let's check it. If you differentiate the profit expression the second time, you get this, and this is always negative, no? Which means when k is 400, right? When k is 400, actually p attains a relative maximum. And now, to find the maximum profit that you will get, you simply put in this 400 into the expression for profit. The expression for profit is actually here. And then you get the maximum profit to be 16,000. Okay, here write a bit more to justify that this is actually the absolute maximum. You also want to notice roughly know that this gradient expression, right? This the derivative of p. You want to realize that actually for k lesser than 400, right, this expression is actually positive. For k more than 400, right, this expression is going to be negative throughout. So based on this, right, it increases all the way until k equals 400, and after it starts to decrease. So from there, you can also deduce that when k equals 400, p actually attains its absolute maximum as well. So with this, we have come to the end of chapter 3 notes.